and a small group of passionate and innovative students came together to create Formula SAE. This competition, then held between only 4 teams, has grown into an international competition for much more than just combustion-powered vehicles. This year, for the first time ever, Longhorn Racing will be unveiling 3 completed vehicles, a combustion, electric, and solar-powered vehicle. I'm so pleased to present the hard work that our students have dedicated over the past several months. But first, we'd like to have a word from the people who started it all. I'd like to introduce Dr. Ron Matthews.
Welcome. So I'm going to give you an abbreviated version of the presentation that I gave celebrating 20 years of Formula SAE last year. And so, like I said, we started Formula SAE right here at the University of Texas back in 1980-81. So what did the teams not have during the 4 years that we hosted the Formula SAE competition? One, there was no internet. There was no internet until 1991. There were personal computers. The Apple II came out in 1977, and the IBM PC came out in 1981, but neither were widely available for a long time. In fact, back in the day, if you had a handheld calculator, you were big time. Okay, there were no cell phones. They were demonstrated in 1973 and admitted to market in 83, but they cost $3,500, so no students had one, and I didn't have one. There were no engineering tools to design and develop race cars, so computer-aided design and simulation software, so there was no MathWorks, no MATLAB, no Simulink, no HyperWorks, no solid modeling such as SolidWorks, no aerodynamic modeling packages, no engine intake for exhaust tuning programs such as the Carter Wave that our team uses, no intake restrictor optimization programs, no suspension design programs, no race simulation programs. Now the teams have all of those types of software packages available, but not in the early days. Also, the tools that were available to fabricate the race cars, there was no MIG welding, so that first came out in 1994. Computer-aided manufacturing. There were numerically controlled machines in the 70s. Computer numerically controlled machines at reasonable cost didn't come out until the mid-80s, so the first 4 years we didn't have access to them. Plasma jet cutting was invented in 1957, but wasn't generally accepted until the mid-70s. We did not grow a population until the mid-80s, so again, our team didn't have one, neither did any of the other teams. No water jet cutting was patented in 1987. No rapid prototyping or rapid manufacturing, that came out in 1992. No aftermarket user programmable onboard computers. Almost no commercially available parts for Formula SAE size race cars. No fuel injectors appropriate for Formula SAE size engines. Okay, so what kind of prior student competitions were there? In 73 and 74, there was a competition called Recreational Ecological Vehicle competition at the University of Cincinnati, and died after 2 years. In 1976, there was the first mini Baja competition, which is now Baja SAE. So we decided on those engineers liked our branding of Formula SAE and adopted that branding for what was mini Baja and is now Baja SAE. So mini Baja started in 76. In 1979, there was a mini Indy competition conceived and hosted by Dr. Kurt Marshak at the University of Houston, and he later hired him away from the University of Houston, and he retired quite a while ago. All entries in Mini Indy had used a stock, unmodified 5 horsepower Briggs & Stratton single-cylinder engine, but it was asphalt racing, so that was first asphalt racing competition. In January 1980, I joined the mechanical engineering faculty here at UT, and immediately started the UT student branch of the Society of Automotive Engineers. And we had very enthusiastic students, some of whom are out here in the audience right now, who wanted to go, built a car to go to Mini Indy, only to find out that Mini Indy died after the first year of it. And so they generated the concept for a new intercollegiate student engineering design competition that was going to be asphalt racing again. So Robert Edwards, in the audience, and John Telkamp led a discussion among UTSA members and envisioned a competition that would involve design and constructing a race car along the lines of the SCCA Formula 440 entry-level racing series that was popular at the time. I came up with the name for the SAE for this new type of race car. So I followed the format of Formula S, Formula A, and Formula B that were also popular at the time. But the name Formula SAE emphasized that it was an engineering competition and not a driver's competition. Okay, and so Edwards and Telkamp and other UTSA students, Bill Green, Dick Morton, who's out in the audience, Mike Best, and Carl Morris, drafted a set of safety and competition rules and presented them to the SA student branch. And to me, I then contacted Bob Seckler, who's retired, at SA headquarters and asked for his permission for UT to generate this new competition and host the competition in the summer of 1981, and he agreed. So Mike Best, Carl Morris, and Sylvia Overdraw, that was the president of UTSA, along with me, began planning and organizing an event to be held in May of 1981. So here it's important to note that Formula SA was not simply a renaming of the Mini Indy competition, because recall, everybody had to use a stock, unmodified, single-cylinder, 5-horsepower Brixton Stratton engine to go asphalt racing. And there were no previous competitions that allowed these students, in fact, required students to pick their own engine. Formula SA required students to pick their own engine, and not only allowed, but encouraged the students to modify that engine. First competition we did that very well. Okay, so we had to send letters to all the other SA student branches in the U.S. asking them to generate a Formula SA car very close from Texas and race against each other. So 16 said they would come, only 4 came. One of those was us, so we didn't actually have to come very far. But I'll show you how to do that now. So here's the rules, 1981. The current rules package is, 100 pages, something like that. This is it for that first rules package. We're glad to be able to carry a person 6 feet tall weighing 200 pounds. So it's cost ceiling $1,750. Brakes had to be capable of sliding 2 tires on dry pavement or stopping the vehicle within 25 feet from an initial speed of 20 miles per hour. The vehicle had to be a student design and construction. The design team could select any 4-stroke single carburetor engine in those fuel injected engines that were appropriately sized back then. And there was an intake port restriction of 1 inch. There were also some safety rules, such as requirement for a roll bar and a driver's helmet, but the original rules were typewritten because, again, no PCs back then. At least then that were portable. And so those rules were handed out to the judges, and duplicated handed out to the judges, and no copies remain. But that was basically it, other than a few safety rules. Okay, so this is the growth over the first 10 years of Formula SAE. I can do this without killing you, right? Okay, so 4 teams in 1981, about 38 teams in 1990, so it grew by almost a factor of 10 in that first decade. There are now more than 650 teams from 50 countries. There are 4 SAE competitions in Japan, Australia, Brazil, Italy, Austria, Germany, England, and 2 in the United States each year. The foreign competitions are held before the U.S. competitions. They will send their very best teams to the U.S., so We have to compete not against just the best teams in North America, but against the best teams in the world. So the Florida SA competition started right here at UT. Has since grown to become the largest intercollegiate student engineering design competition in the entire world. Very enthusiastic students during those first 4 years, and there are quite a few of them out there in the audience. But what starts here changes the world, and UTSA did change the world.
Thank you, Dr. Matthews. Next, I'd like to introduce the professor who has mentored the solar team for decades since the early 90s, Dr. Gary Howland.
Okay, thank you, Andrea. So yes, I am very pleased to be here today to tell you a little bit about UT solar car racing. Since you're going to hear an awful lot about the newest cars shrouded in secrecy right now, I'm going to do a little bit like Dr. Matthews did and talk about our history here at UT. So first of all, the team was founded in 1988, originally called the Longhorn Solar Race Car Team. And I talked to a number of people here today, and I guess because I've been around so long and look so old and so forth, they think I'm the only advisor that solar has ever had, but that's actually not true. The team was actually founded by a mechanical engineering professor, Professor Gary Valite, who is now retired, and a group of very enthusiastic students that decided that UT ought to have a solar car team. UT has now built 8 solar cars. The names of those cars are listed there. It started out with a car named Texas Native Sun, or Texas Native Sun 1. It was preceded with a new car called Texas Native Sun 2. Then came a car named Solstice, followed by Solar Steer, followed by Samsung Solarian, and Texan, and V-Volt, and finally our new car to be unveiled tonight. Longhorn Solar Race Car Team was renamed UT-SVT. I'm sure many particular students have seen that around on our literature and so forth. University of Texas Solar Vehicle Team in 2003 to feature UT Austin more prominently. And finally, I guess 4 or 5 years ago now, UT-SVT merged with LHR, Longhorn Racing, becoming LHR Solar. And that gave us a whole bunch of advantages in terms of resources and ME students and so forth. So what about solar car racing? So solar car racing began in the United States in 1990. A race sponsored by General Motors called the GM Sun Race. And this race started at Disney World in Orlando, Florida, and ended up at the General Motors Technical Center in Warren, Michigan. And UT participated in that race and finished 22nd out of 32. And that may not sound particularly great standing, but in fact it was only 41 minutes behind the winning car from the University of Michigan. So this is 41 minutes out of a 1,000-mile plus race across the country, with 41 minutes separating UT and the winner. So again, this car was called Texas Native Sun. There's a picture of it on the right there. We're kind of sunny in here, but hopefully you can see that. So four-wheel design, very aerodynamic, solar cells curved around the body. Here's a interior view of the Texas Native Sun 1 cockpit on the left. Again, I'm not sure how well you can see the photo, but I'll point out that the entire electrical system consisted of wire, switches, relays, a few fuses, and some digital panel meters. And that was pretty much it. Switches to monitor battery voltage and battery current and things like that, and no sophisticated telemetry, no microprocessors, no computers and so forth. Pretty basic. This car did have a rather unique battery, as shown in the right picture. They are nickel hydrogen batteries, and they were obtained kind of fortuitously because of a delay in launching a satellite. UT was able to procure these light, high-performance nickel hydrogen batteries. Today we use lithium-ion, and pretty much everybody, especially the students, know of the hazards of working with lithium-ion batteries and how careful one has to be. These were also hazardous batteries. As a matter of fact, if the temperature was to go above 105 C on these batteries, those little canisters would explode like little hand grenades. So one had to be very, very careful with this battery pack. So Texas Native Sun was followed by Texas Native Sun 2. Picture of it there on the right, UT's second solar car. It was a larger and heavier car, as you can, I think, tell from the picture, and in fact was designed to be a two-person solar car, so more like a normal car. It had a number of unique things also. It had a homemade hub motor. Very unique, particularly for this time, that was designed here and built out of the Center for Electromechanics. Also, the motor controller was homemade, built by the students working on this project. And this was about the time that I started to stick my feet into the project, and I remember many hours with the student responsible for this controller, trying to help troubleshoot it with a multimeter and the transistors and getting it to work. No printed circuit boards, basically a perf board with point-to-point wiring of the circuits. This car used lead-acid batteries, so it's one of the main reasons why it was quite heavy. Texas Native Sun 2 was entered in the 1996 Tour de Sol. That's a race that doesn't exist anymore. The Tour de Sol existed for a number of years. This one was from New York City to Washington, D.C., and Texas Native Sun 2 finished fourth in its class. The biggest excitement on this race was the car lost completely all of its electrical power in the Holland Tunnel between Manhattan and New Jersey. Caused quite a mess. Students pushing it out, and that was the big excitement for this race, and probably for the car itself. car was called Solar Steer. And Solar Steer was our first car to use lithium-ion batteries. And really the first car that I was involved with from the ground up. Picture of it there on the right. It competed in Formula Sun Grand Prix. So this is the, now moving into the main race that exists today. Formula Sun Grand Prix is a track race. And this was held at the Texas World Speedway. The person leaning over the car there is actually in the audience with us today, one of our alumni, Jerome. And one of the aspects of this picture also to point out, and again, you probably cannot really see it with our viewing conditions, but the fact, and this is kind of a warning to our new students, that you never have a Formula Sun Grand Prix without rain. And it is actually pouring rain in that left picture as Jerome is working on the car. Our next car was called Samsung Solarian. Samsung got the naming rights because they donated $75,000 for its construction, which pretty much was the money that we used to build this car. Samsung Solarian also used lithium batteries, a very good hub motor, and like pretty much all our solar cars, electronics built by the students. Samsung Solarian gave us our first, to my knowledge, top 10 finish in a race, 8th place in Formula Sun Grand Prix 2009. So hopefully our new car can beat that, maybe first place finish in Formula Sun Grand Prix 2022. So for that 8th place, it completed 199 laps, so over 300 miles in the 3 days of track racing, and actually achieved, of all the cars, all the entries, the second fastest lap at a speed of a little over 40 miles an hour. This car also competed in the American Solar Challenge 2010. So American Solar Challenge is a cross-country event. A cross-country event that's driven on normal roads, obeying all normal traffic rules. So it used Formula Sun Grand Prix 2010 to get into this race, and then entered the cross-country race, which was from Tulsa, Oklahoma to Chicago. So a long cross-country race where there were 17 teams that tried to get in, and 13 that actually qualified. The picture on the right shows Samsung Solarian actually finishing this race, and very excited students running beside the car in a little town just called Naperville, Illinois, just outside of Chicago. Okay, so last car that I'd like to talk with you about today, called Texan, quite a successful race car. And I remember one day, I guess a couple of years before this, I was reading on a Saturday morning the Austin American Statesman, and saw an article that there was this track coming to Austin. And that track was the Circuit of the Americas, and I immediately knew that we had to do solar car racing there. And actually, UT has been very instrumental in making that happen, with staff and others having multiple meetings with the COTA personnel and just getting this all organized and set up. And indeed, we did make it happen, and there's been a number of solar car races out at COTA. I'm sure there will be another one in the near future. And Texan competed in Formula Sun Grand Prix 2013, 2014, 2015, and 2017, all at the Circuit of the Americas. Also in 2014, we competed in an American Solar Challenge, an ASC race, from Austin to Minneapolis. And so for all of these track races, all of the Formula Sun races at COTA, we have been the university host. After the race, typically, I think in all cases, having the awards dinner here at UT, usually in the Union, and showing people around our campus. And we were also the university host for ASC 2014, and indeed had the start of the race right here on campus. So if you can see that picture, you'll see it's the circle now down close to San Jacinto. And so this the right-hand picture is the start of the ASC 2015, right from UT. So that was a lot of fun and pretty exciting. The left picture shows us en route, I think maybe in Oklahoma. Very hard to see, I'm sure, but there is our lead vehicle, a little green Honda Insight that a lot of our current team members are familiar with, followed by Texon, our solar car, followed by our chase vehicle en route on ASC. Okay, so in wrapping things up, UT Solar and LHR in total has certainly a history of innovation. Tremendous work by our students, almost all of whom are undergraduate students. And I list there just some of the things that our students have developed over the years. Battery management systems, very, very sophisticated BMS for battery packs. Array fabrication, we now fabricate our own solar arrays. PowerPoint trackers for managing the array power. Motor controllers, we have designed and built several motor controllers. Lots of work on telemetry, sending data from the solar car to either the pit or to chase vehicles. Control systems, multiple control systems. And lots of non-electrical stuff. Carbon fiber composites, mechanical systems, basically all designed from the ground up by our students. So tremendous job, and I'm really very, very proud of everybody. And of course this provides tremendous experience, practical knowledge that get lots of feedback how it helps people when they leave UT and go off for their careers. So thank you. It's been my pleasure telling you a little bit about solar, and I will pass things on.
Thank you, Dr. Hollick. Lastly, I'd like to express our gratitude to all our supporters. Thank you to our Unveiling partners who helped us to be able to put on this event, and to all the families, alumni, and all those gathered here who continuously showed their support. But most of all, thank you to our corporate partners, especially to our title partners, Chevron and Cumberland Additive. Before we unveil our cars today, we will be unveiling the competition gear that we will be using for this competition as well as for many competitions to come, thanks to Chevron. I'd like to introduce Cockrell alum and the UT Executive Champion at Chevron, Mr. Eric Zergo.
So my name is Eric Sergo. I'm the Vice President of Facilities Engineering for Chevron. I'm out of the Houston office. I'm here with my wife today. We're both Longhorn graduates from Mechanical Engineering School in 1987. So really cool to be here today. First thing I want to do is I want to recognize Andrea. She's president of Longhorn Racing, and I want to recognize her and her team for what they've accomplished this year. This is absolutely incredible, so congratulations. And then second, I want to recognize Michael and the faculty here that have been sponsoring what is the premier racing program in the world from the University of Texas. And I think Dr. Matthews with his mic drop, I saw the mic drop and the walk off the stage is clearly right. I mean, this is the premier program, and it has changed the world in student competition and student teamwork. And so I want to recognize Michael and all the faculty at UT for such an incredible program. So Chevron has a long history at UT. We've been involved in the school for many, many decades. In the last 40 years, we have contributed over $70 million to different engineering and education programs in the university. Some of them you may have heard of, and some of your family may have been involved in, but we're involved with Women in STEM. We're involved in the Energy Institute. We have over 350 research projects we funded. We're part of the 40-acre scholarship program, GeoForce, STAR research program, and then student veterans we support post-graduation. But one of our premier programs is Longhorn Racing, and this is the one that we just think the world of, because it is truly showing energy transition in motion. We're going from an internal combustion car to a solar car to a battery-operated car, and Chevron is leading the way in energy transition, so we're really proud of this. Before we unveil the cars, I'll just point your attention to, these are the fire suits that are required for the drivers. Chevron sponsored the fire suits this year, so we got to work with the team on branding, and I believe they've been working with the fashion department here at the University of Texas. And so the drivers, I think there's 3 drivers per car, will all have fire protection suits that Chevron's provided. And then we've got the polos, the young lady here is wearing for the traveling racing team. So we have a really nice branded looking group of young women and men who will be representing the University of Texas at the races. So congratulations for that. And just last statement, I want to recognize the students and faculty. This sort of teamwork, when you take something from concept to design, to scale up, to pilot, to application, to a race, it's pretty amazing. And they do it in a very short order of time. They have multidiscipline teams. This program cuts across dozens of departments and degrees and disciplines in the university. And so these kids come together, diverse group, diverse thinkers, and they put their heads together and they produce winning concepts and winning models. So here's to bringing home some hardware at these races. So good luck to them.
Thank you so much, Mr. Sergo, for your support. And now, what we've all been waiting for, I'd like to welcome the electric team to the stage.
Hello, everyone. First of all, I want to apologize for my voice. It's like my body knew that I'd be giving a speech today and wanted to pull a prank on me. My name is Srini Tupuri, and I'm the team captain of Longhorn Racing Electric. Before I talk about our vehicle, I want to introduce our amazing leadership. Our chief engineer is Daniel Wen. Our operations lead is Ellie Sun. Our aerodynamics lead is Stefano Bonilla. Our bodywork lead is Igor Souza. Our dynamics and structures lead is Kieran Cosgrove. Our powertrain lead is Joseph Vickery. Our electronics lead is Dakota Britton. And our race logistics and testing lead is Jake Highland. The competition that we designed for is the Formula SAE Electric competition, this year held in Michigan in June. As a part of the FSAE competition, there are both static and dynamic events, and there are 3 static events. First is design, where the team members are grilled by experts in the field on the design and analysis of the vehicle. There's business presentation, which is a case comp style event where we pretend we're a small business that is selling our product. And there's cost, where teams compete to build the best vehicle for the lowest cost. There are 4 dynamic events: skid pad, autocross, acceleration, and endurance. The car is tested in its cornering abilities in skid pad, straight line acceleration, its maneuverability in autocross, and its reliability in the 14-mile endurance event. On the screen here, we have some of the old tracks, the endurance track from 2019 and the autocross track from 2017. And these tracks are a surprise each year, and they tell us basically competition day or a few days before. So to give some history on the team was founded in 2016 by a group of 15 students. Since then, we've grown to over 80 students and are now one of the best electric teams in the nation. In the 2019 competition, we placed 7th and were one of 4 teams to finish every single dynamic event. In the 2020 virtual design event, we successfully completed we got best team in our design bay. This year, coming out of COVID, I'm really excited to show off all the hard work of our engineers and outperform all of our previous years. All of our team members have put in countless hours of design, manufacturing, analysis, and assembly in order to get where we are today and get us to competition. And the leads will give you a further glimpse into some of the engineering challenges and design decisions that led us to our final design. Daniel, our chief engineer, will be going over overall vehicle goals, and then we'll be going into highlights of each of the systems. So without further ado, it's my honor to unveil the 2022 Longhorn Racing electric vehicle, Easy Driver.
Hi everyone, my name is Daniel Nguyen and I'm the Chief Engineer for the Longhorn Racing electric team. Today I'm extremely excited to share with you some of the design insights and highlights behind the vehicle that you see here today. So coming into this year, we faced a challenge common to many FSAE teams across the nation. After 2 years of designing cars virtually over COVID, we ended up with a team comprised of 80% underclassmen going into this team. Anyone who's designed a race car knows it's a huge challenge to design even with a team of experienced engineers. And going into this year with such a large number of people designing a race car for the first time was a monumental challenge. However, I believe that all of these underclassmen and all the other members have risen to the occasion, and we've designed a vehicle capable of performing in the top of the competition that we're entering this year. So a huge shout out to all the undergraduates and all the upperclassmen who have done wonderful this year. So now I'm going to share just a few technical highlights about the vehicle and contextualize some of what you see there. So the goal with this vehicle was to perform in the top of the endurance event. As Trinity mentioned, there are several key dynamic events in the FSE competition: the endurance event, autocross, skid pad, and acceleration. Our team saw the endurance event as the event to score the most points in the competition, and as such, we designed the vehicle around performing the best in that category, although it's a strong contender in the other categories as well. If you take a look at the car, you'll notice an extremely low CG height and extremely low weight as well. The weight for this year's car is only 500 pounds and the CG height is at 11 inches. Just to give some context about where we stood a couple of years ago, our previous car weighed in at about 600 pounds and a CG height of 15 inches. So that's a massive change and improvement from previous years, and we think that those improvements will pay dividends in the competition. Something else that you'll see is a very low aero package, and we intend to make use of the extremely low area between the front wing and the ground to take full advantage of the low profile to produce more downforce in the front that's efficient. With this came some challenges in the suspension design and aerodynamics integration that we sought to address this year. Any of you who have followed F1 know that porpoising is a very prevalent issue that they face in F1 these days. And we're not immune to those issues as well. So our suspension team and dynamics team have been hard at work developing models to characterize and design around the stability of the vehicle in order to take full advantage of the aerodynamics package. Something else that's a huge highlight for this year is the interesting placement of the CG on our vehicle. We've deliberately chosen to bias the CG to the rear of the vehicle in order to make maximum use of the traction in the rear. Since we run a rear-wheel drive car, one of the limitations of being able to output more torque to the ground is the stability of the rear in corners and in acceleration. So by biasing the CG to the rear of the car, we're able to exceed normal amounts of acceleration that you get from a typical 50-50 bias in SAE. And you'll also notice that we have an extremely large rear tire compared to other FSAE teams. And that's a deliberate decision made in order to deal with the stability issues as well as take full advantage of the track deployment. Our car also features very interesting points of adjustment, as we recognize that in the design of the vehicle, it never really turns out the way that you design it once you build and encounter all the tolerance stack-up and other factors that go into building the vehicle. As such, we designed adjustability into the vehicle in order to take advantage of being able to tune our vehicle into the operating range that is most optimal, even though we haven't been able to hit it perfectly with manufacturing. So through these various strategies, we produced a car that I think will place extremely well in the competition, and I'm extremely proud of all the work that everyone in our team has put together. And now I'll pass it off to Igor to talk about aerodynamics.
There's definitely a lot of people here. Okay. Hi everyone, my name is Igor, and I'd like to highlight the unique features of this year's aerodynamic package. It was designed to be light, easily manufacturable and efficient, but also accounting for the lessons we learned from the past. This year we focused heavily on system integration. Aerodynamics as a performance system has to be a very clear goal in mind in order to optimize the dynamics of the car in corners and also in acceleration. It was only possible for the extensive use of textbooks and computational fluid dynamics. With such a high load in a 12 kilogram aero mass target, we employ carbon fiber extensively for our parts. Similar to our last vehicle, our wings are made of carbon fiber shells with internal gerbs and spars, which we iterated from our past design to reduce weight and improve manufacturability. We expect this car to hit 124 pounds of downforce at cornering speeds. I would like to take a minute to showcase some of the brand new features included in its aerodynamics package. The first one is, as we mentioned in the past, we've suffered from the lack of data that the aerodynamics package produces. So this year, we've implemented a load cell measurement system by isolating the load path of the airfoils through two force members, and we can measure that for load cells. This gives us active telemetry data for the track, and we can optimize our air package around it to give the vehicle the best performance it can. Additionally, one of the key features is also the adjustability of angle of attack. This allows us to have different setups for each competition. We can adjust our wings to have low angle of attack, low drag configuration for acceleration to have the lowest time, and also increase for a high downforce configuration for endurance to have highest cornering speeds. Before I pass on to Kieran to talk about suspension, I'd like to give a big shout out to all aerodynamic systems to make this possible, especially Sean Habibi and Stefano Bonilla.
Hello everyone, I'm Kieran and I'm the Dynamics and Frame System Lead this year. So some of you might be wondering what the dynamics is on the car. So for us, we define the dynamics to be the suspension, steering, and unsprung assemblies here on the car. So based on that, how did COVID impact our team? So at Dynamics this year, we have 13 members. Of those, 2 are returning members, including myself. So a lot of people on our team really stepped up this year. We had 2 freshman subsystem leads, big shout out to them, and we were able to pull off a really cool new design this year. So as everyone's been talking about, we had really good aero and suspension collaboration. We were able to set the ride heights, stiffnesses, center pressure, and tire selection were all bundled together to get the parameters that we wanted for our suspension and aerodynamics. So with this, another big change going in this year is actually the battery packaging. So previous years we've had a flat pack under the driver. This year, the battery is behind the driver. So with that change, it's actually pushing the driver forward and the battery backwards, just moving everything else around in the car and causing major packaging changes. Oh, there we go. Packaging changes on the car. So, as you can see here on the right, this is the entire dynamic system on the car. So we have the wheels, suspension, and steering. On the left, you can see our rear packaging or suspension. So this is our some highlights of our suspension and steering system in the front. You can see we went with a front pull rod system along with our rear pull rods. So we actually opted in to have our shock and buckling packaging completely under the driver's legs. It's not pictured here right now, but there's actually a closeout panel over this, so that way the driver's not at risk from any of these moving components. So what else is new? We have a continuous adjustable ARB in the front with the blade here. And with that, we're able to tune our car really well to have the performance we want on the track. And you can see here a top view of on the right side, you can see a top view of our front suspension as well. So as Daniel was mentioning, we actually have a rear wheel drive car. So what does this mean for our wheel packaging? So you can see here on the left, this is our rear wheel assembly, and in the middle is our front wheel assembly. So because we have the rear wheel drive, we have brakes mounted off our differential directly on the inboard side, which is why you don't see a rotor and caliper on the rear assembly. So the rear powers the hub directly through a half shaft here in the hub, and in the front we actually have the caliper and rotor directly mounted onto the hub and upright, pictured here off the car and on the car. So on this cross section here on the right, the top one represents the rear and the bottom one represents the front. You can see the complex packaging of the lots of components that is not really going to be visible in the car. So this is something I want to highlight here now. Some other highlights of the design are the design for manufacturability and assemblability. So we had major improvements in both those fronts. Another thing we added was adjustability on the system. We have the ability to adjust our Ackerman, toe, camber, and all other different suspension parameters. Another thing we did this year is lower the weight of the front assembly. So by changing our bearings and our pocketing strategy, we're actually able to save a few pounds off our front unsprung packaging this year, as shown here. So our frame. So what exactly is the frame on our car? So the frame is how all the different components are connected together. And it also needs to package the driver. On the section view here on the right, you can see the driver layout within the car, with the battery here on the bottom here, with the driver here, and pedals here in the front with the steering wheel. So our braking and steering system are all completely mechanical. If the electrical system was to fail, you can still use both systems. So some other things that really drive the frame design are the rules itself. So they really don't want the driver getting hurt. So a lot of the frame design is dictated by the rules. What we can really do in terms of innovation in the frame is moving the packaging around and getting everything located exactly where we want. So with this year we had some pretty big improvements as far as accessibility. Everything was much easier to mount and access in the car, so you can put the car together and take it apart really easily. The other thing is the CG location, like Daniel was mentioning. With this new design, we're able to hit 11 inches because everything is as low as possible in the car. Moving on to manufacturing here. So on the left, this is our upright and hub nut and hub manufacturing. They're all done in-house using CNCs and lathes. To highlight more in the middle, in the right here, represents our frame manufacturing process. So our entire frame this year was made of 4130 chromoly steel and welded in-house using TIG welding. So this is a major decision based on supply chain. We actually planned on using mild steel. There's major supply chain issues regarding square tubing and mild steel, which forced us to make these changes. Despite all of this, we were able to have a timely delivery of 3 weeks of our entire frame and able to get all of our welding and everything else done in time for everyone else to start mounting this stuff to the car. This is a huge shout out to our welders, Ben, Luisa, and Reyes, first-time welders, and we're able to put together the car quite well. So huge shout out to them for learning and getting us that. One final thing I'd like to talk about is the frame jigging here. So we used a laser cut wooden frame jig. This is how we huddle all the tubes together while the welders we're putting everything together. In the middle here, you see our suspension jig. This is to hold our suspension points in a relatively stiff configuration so we can get the suspension parameters we wanted. So overall, our jigging saw major improvements in terms of accuracy and precision of our frame. With that, I'd like to hand it off to Joseph.
Hi, yeah, so I'm going to be talking about the powertrain now. This is just a quick overview. So for us, we define the powertrain as the drivetrain, the battery, and the cooling for those systems. And the goal for this year was to minimize the complexity whilst maximizing the performance. In our assembly itself, if you open it up in SolidWorks, 3/4 of the assembly alone is battery parts, and that's not even all of powertrain. And the biggest struggles we really faced this year were, along with everyone else, and mainly for electronic components, were the supply chain and part procurement. However, I think powertrain electronics did a great job of handling this and working together more than we ever have in the past, and really knocking it out. And before I show you some of the cool stuff we've been working on, some of the more individual components, I'll just go over the numbers everyone's really interested in since it is an electric race car. So our battery has a pack voltage of 402 volts and a capacity of 6.9 kilowatt hours with the capability of drawing over 200 amps. Just to put that into perspective, that pack capacity is about a 1/15 of a Tesla's battery. And for our drivetrain, we went with a rear-driven single-chain drive setup with our one motor, and our max power draw is 80 kilowatts, which is about 108 horsepower, and our max torque is 240 newton meters, which is about 180 foot-pounds. And our top speed is 75 miles per hour. It could be faster, but that is what we've geared it for the competition. And our acceleration time is 3.8 seconds, which puts us in the trends in the past year's competitions, about the top 3 for that event. Now moving on to the battery. To make up that whole pack capacity and voltage and all that, it requires 480 Samsung 2170 cells. So those are shown in the top right. A lot of cells. And here on this whole slide are some of the pictures from our manufacturing. So that top left image is our segment plates we use to hold the cells themselves, to keep them safe and to constrain them. We had machined all of these before the spring semester even started, and really it came down to waiting for the cells to come over spring break. So that's what I really go over by difficulties in part procurement and supply chain. They were just stuck in a bay in Los Angeles doing something. So once we got them, we stayed over spring break and got it all assembled in that week, but that whole 3 months was just empty time working. And the bottom left little GIF is from nickel fuse testing. We did a lab here at UT. And then something I'd like to highlight, the 2 bottom right images. This year something we did different was actually making a test segment. So since we had to wait on the cells, we took that time to make a test segment with some of the old cells we had and figure out if there was any difficulties with assembly or anything, and we implemented those changes before the cells came in. So we were really able to just knock it out during spring break. And that bottom right image, which it's kind of hard to see. I thought the projector would be bigger, is a thermal image camera to check the high current path after we had made the test segment. So here's a little bit of the final assembly. So you can see them packed all into the case there on the left. In the middle picture is the entire case with all the stickers we need for rules. And then that right one is just highlighting one of the welds we did on the case since we made it in-house. Shout out to Ben. So hand in hand with the battery is the cooling you have to do for it. So for this we went with forced air convection. On the left you can see that's why the case has all the holes to actually force the air through. And then that middle one is actually a CFD simulation we did hand in hand with some of the hand calcs we did. We worked a lot with the Aero subsystem, so they were very helpful for that. And then on the right is a air-cooled versus water-cooled test. As Kieran was saying, with some of our packaging constraints, we were trying to go explore water-cooled this year, but because of the space we had, we couldn't really do it in the way we wanted, and basically the line at the bottom is cooler, and that's the air one, so that's why we went with air this year. So now I'll move on to the drivetrain. So something I'm really proud of with the drivetrain this year is that before the spring semester even started, every single part except for one was already manufactured. So that was ready to go immediately as soon as the frame was ready for it. So for some context, on the left is a motor mount, in the middle is a differential mount, and then on the right is the motor output shaft. So that's actually 17-4 stainless heat treated, giving it that nice fancy golden color. So finally here are some pictures of the actual assembled motor and drivetrain assemblies, shown on the left and the right, and in the middle is the setup for the motor for electronics to do their testing when hooking it up with the inverter in our VCU. And it's not really shown here because it's a little hard to picture, but for the motor and inverter, we use a water cooling loop through a radiator and a pump. And I would suggest everyone, like once this is over, you can come take a look at the car. All this stuff is kind of easier to see on the car besides the battery. That's mainly why I had a lot more photos of the battery than this. So yeah, feel free to come take a look and ask us any questions if you have anything you want to ask. I guess just lastly, I'd like to give a shout out, as all the other people have been saying, to all our members putting in a lot of hard work, basically like sleeping at the research campus this whole week to get everything done. And then when we're not doing work for Powertrain, doing work for the other systems. 2 of the 3 welders are from Powertrain. We also made a lot of parts for the other systems. So big thanks to everyone, a lot of work this semester, and pass it off to Dakota.
Thank you, Joseph. Hi everyone, my name is Dakota Britton and I'm the electronics lead. The main goal of electronics this year was to design a system that's as simple as possible while also providing functionalities to make the car safe and to improve the feel of the car for the driver. So in order to keep our system as simple as possible, we decided to use a few off-the-shelf components from a company called AEM. So here we have our vehicle control unit, our dashboard, and our battery management system. We had originally planned to use a custom vehicle control unit with the Orion BMS2, but due to supply chain issues, we decided to switch over to these components. And the nice thing about these components is that they all integrate together seamlessly using the CAN communication protocol. So in addition to these off-the-shelf components, we also designed a few PCBs of ourselves. So I'm not going to go through too much detail here, but to list a few of the features that we implemented, we have brake plausibility checks to make sure that the brakes are operating properly. We have DC-DC conversion to power our cooling from our high voltage battery. We have contactor control, discharge and pre-charge circuits, and that nice tractive system active light that's glowing at the top of our boot there. Alright, so this year we put in effort to improve our harnessing because in past years the harnessing had been a little messy, and this year we wanted everything to go smoothly, we wanted it to be well documented, we wanted it to be easy to maintain, and we wanted it to look good. And I think we did a pretty good job there, so I decided to showcase some of our bundles here. It's a little hard to see now that I look at it. And I also included a picture of our Dakota lithium battery because it's got my name on it. And finally, in order to make our car as safe as possible, we have a network of switches all around the car called the shutdown circuit that shut down the car in the case of an emergency. So on the left there we have our schematic of the shutdown circuit, and the details don't matter too much, but some of the switches that we have there are master switches, e-stops, fuses. We have an isolation detection switch that detects if the high voltage battery is connected to the frame, which is not a good thing, it shuts down the car in that case. And yeah, this all keeps the driver safe in the case of a crash or any other emergency. So that's all I have for electronics. I hope you all enjoyed. Now I'm going to pass it off to Srinidhi.
I'm actually going to hand it over to Ellie for a quick shout out for operations.
Hello everyone, my name is Ellie and I'm the operations lead for Electric. I just want to let everyone know that we have some really amazing merch located in the back table in the corner over there. including a really awesome electric sticker if you would like to purchase one. In addition, I also want to give a big shout out to all the operations team members. Thank you so much to everyone on corporate relations, public relations, events, treasury, and outreach. Thank you guys so much for your hard work.
And thank you to LA for completely transforming operations. When the team started out, we probably had like a one-person operations team, max 2, and now we have like a complete team helping us get through all of the operational tasks. So huge shout out to her as well. And I also want to thank the team. I'm so incredibly proud of all of the hard work and dedication of all of our team members. And we also wanted to thank all of you guys for supporting us every step of the way. After the end of the event, please come by and take a closer look at our car and ask us any questions that you may have. I will now pass it on to Solar.
Well, thank you, Trinity, for that amazing introduction. And that's a cool looking race car, am I right? Hello everybody, thank you for being here. My name is Rishi Panakanti. I am a third year electrical and computer engineering student, and I have the privilege of being this year's team captain for Longhorn Racing Solar. Dr. Hal, our faculty advisor, gave you an amazing history of our team, so I'm not going to go more into that. But we've been around for a while here at the university. We've built some amazing solar vehicles, and we are really hoping to carry on that tradition. I joined this team the fall of my freshman year, so the fall of 2019. I had no previous interest or inclination of joining an automotive vehicle team. I had no interest in solar energy. But I joined because a friend of mine said, hey, let's go to this org event, that'd be cool. And I conform very easily to peer pressure, so I went. When I went to the first work day up at the J.J. Pickle Research Campus, there were somewhere under 20 members present. And among those, only 3 of them were on our mechanical team. So yeah, that's right. 3 people were building the entire mechanical systems for the solar vehicle. Since then, in the past 3 years, I have had the honor of watching this team grow to over 50 of some of the most passionate, dedicated, and intelligent students this campus has to offer. And we are still growing strong, and I'm very, very happy from where we've come. All right. So, some of the students that really make that possible and make this team so amazing are our system leads, and I'd really like to give them a shout out here. So Esther Jin is our body lead, Jacob Yan is our dynamics lead, Manthan Vidyaya is our BPS lead, Siddharth Babu is our controls lead, Afnan Mir is our power generation lead, and Siobhan Madden is our power systems lead. And please, a huge round of applause for these guys. This is amazing. They have all poured their blood, sweat, and admittedly a few tears into this vehicle, and I'm so very happy that we're able to unveil it to you today. So with that, I'd also like to thank all of our alumni, some of whom are here today. Like we mentioned at the beginning, our competition rotates on a 2-year cycle. So we deal in the American Solar Challenge, and what that means is every year there's a track race, the Formula Sun Grand Prix that Dr. Howard talked about, and every other year they host an American Solar Challenge cross-country race. So we build a car every 2 years, and what that entails is that there's some students who were part of the initial design cycle that have since graduated, gone on to full-time jobs or graduate studies, and we're not here to see us complete this vehicle. But I'm very proud to be able to present it to them today to show them really what an amazing thing they have created, not only just the design of the car, but also the team and where it's come from since they've left. Next, I'd like to thank all of our corporate partners. This project takes a lot of resources, and it would not be possible without all of the ongoing support from all of our corporate partners. So seriously, a sincere thank you for everything that you've done for us. And lastly, but certainly not least, I'd like to thank Dr. Halleck for his amazing support through all his years with the team. He's been the backbone of this organization for so long, and I know that we would not be where we are today without him. So another huge round of applause for him, please. So, with all of that said, I'd like to take you to what you all came here for today. And it is my insanely distinct and complete, whatever word you want to say, honor to be able to unveil to you the 2022 competition solar vehicle for Longhorn Racing Solar, Lone Star.
Hi, so I'm Clark Poon, and I'm the chief engineer for solar. And I'm going to go over some of our design considerations. So, in order to understand our design process, first you have to understand some of the restrictions our car faces. So, first in our competition, all of the cars are scored based on lap count. So, over a 3-day period, the cars will race for 8 hours a day, and you place based on how many laps you do over that period, right? So 24 hours total. And the cars have to be completely powered by solar power, right? So it's a solar car race, so this makes sense. The solar array is also limited to 4 square meters, which means that the amount of power we got out of the array is similar to what you need to power a low-end household toaster. So not a whole lot, right, but enough to toast some bread. And our battery is limited to 20 kilograms, so we can store some of the solar energy, but they want it to, it's a solar race, not an electric car race, so this, we can only store about 6 hours of energy in our battery. So with these restrictions in mind, one of the big goals of our design process was to make an efficient solar car, because this is an endurance. We call it an endurance race because it goes over 24 hours. So you need to have a very efficient, very light, aerodynamic car, so that you can be very energy efficient. And our electronics also have to be very low power, so that all of the energy we get out of the solar array, we have to use it the best way possible, right? We don't want to waste any. Because again, we just have enough power to toast some bread. So our second design goal was we wanted to make a very manufacturable car. So for the previous build cycle, we had made a very ambitious car that had like a single big piece for the body, but it turns out this is very hard to manufacture. So going into this design cycle, most of our engineers were new incoming students with less experience, so we decided to make something that was easy to produce. So on the mechanical side, this meant creating a body that was multiple simple to manufacture parts that can then be assembled together, as you can see here. And on the electrical side, this meant we reused some of our electrical systems and just upgraded them. So for example, our battery protection system, or in industries usually called the battery management system, is mainly an improvement on our previous design. But for some of our electrical systems, we did completely redesign like our control system, because it didn't meet our requirements. So now I'm going to pass it off to Walter, who's going to get into more of the details for our mechanical system.
Hello everyone, my name is Walter Stark. I am a second-year mechanical engineering student, and I am this year's mechanical lead. So starting off, as Clark previously mentioned, one of our main goals for this year was manufacturability. And in previous years, we had trouble finishing our car. In our last car, Beeble, we didn't end up completing it due to a lot of manufacturing issues in the smaller team. So with that, we opted to go for a monohull design, which is similar to that of what boats are shaped like, so that we could get both aerodynamics and also we'd be able to manufacture it easily. As Clark also mentioned, we opted to manufacture our car into a lot of smaller different components. As you can see here and also on the screen, we have 5 different components that you can see. The first is the canopy, which can be seen on your right, and then the nose, the bottom hole, the tail, and the top shell. All of these parts are made out of carbon fiber, with the exception of the interior of the canopy, which is made out of Kevlar so that it is shatter resistant, so that in the event of a crash, the driver will be well protected. Next, within this body system, there are also the frame. So the frame itself is made out of 661 T6 aluminum. We chose this as opposed to some previous years of using steel because of its light design and also because of being able to avoid some of those supply chain issues that some of the other teams have mentioned. So some of the requirements for this year's car are that we have to do a bunch of load case scenarios, including a rollover event, a side collision, a front and side collision, and a back collision. So our frame we designed to be the safest possible and make sure that the frame itself has minimal deflection in the event of a crash to save the driver. And the last portion of our body system is enclosures. So enclosures is mainly responsible for a lot of interior boxes within the car. The main being, which you can see on the right image here, is our battery box. The battery box itself contains 2 different modules. One module is shown here, and that allows us to easily keep all of our battery parts compact, while also being able to have a lightweight design. This year, we opted for our battery box to be made out of Kevlar, so that we can have a lightweight yet strong and protective battery box, so that in the event of an issue with the battery, the driver would be able to have the maximum amount of time to exit the vehicle so that they would not get hurt by this battery fire. And then lastly, for enclosures, is this electronics box, which allows us to keep all of our PCBs in one designated area so that wiring can be a lot easier and in one concentrated place. Another system that is under the mechanical systems is dynamics. So starting with dynamics, there's a subsystem called steering. This year we opted for an Ackerman steering design to allow us to have one wheel that is on the interior of turning to have a larger turn angle than the outer wheel, allowing us to take corners easier. And we also opted to use a rack and pinion design due to its small footprint within the car. Next in dynamics is our unsprung mass. On the right here, you can see our braking system. So overall, just to explain what unsprung mass is, it's everything within the car that isn't steering or isn't on the suspension. So on the right, as I previously stated, is our braking system, which has 2 cylinders, and on the farthest left image, you can see our brake calipers. So for our braking, we opted for 3 brake calipers per both of the front wheels to give us superior braking compared to other solar vehicles, and also to equally distribute the weight on the tire itself. And then the last portion of unsprung mass is this hub here. I'd like to give a huge shout out to Jacob Yan and Nathan Lee, who spent countless hours in the shop, some days up until 3 a.m. manufacturing these hubs. And yeah, if you could give them a huge round of applause for that. Okay, and then the last portion of our dynamics is suspension. So as can be seen on the farthest right image is our front suspension. So our front suspension, we opted for a dual wishbone setup, which is similar to a lot of race cars to give us greater stability and also greater cornering ability compared to other solar cars. And then since we focus mainly on the design of that, we opted for a suspension system for our back wheels that is a lot similar to a commercial car, so that we could spend more time on the designing of our front suspension instead of our back suspension. And with that, I'm going to hand the mic over to Hannah for our electric subsystems.
Hi everyone, thank you for coming. My name is Hannah Lee, and I'm a third-year electrical and computer engineering student here at UT, and then also the electrical lead of Longhorn Racing Solar. I've been a part of this team since my first semester in college, nearly 3 years ago. And in that span of time, it has been amazing to see the growth of the team and how far we have come. Day in and day out, Solar's electrical team has spent a countless number of hours to make this car a reality. From the solar cell array that makes this car a solar car, to much of the hardware and software that allows this car to operate both correctly and safely. Much of the vehicle's electrical system is custom, designed, manufactured, and tested entirely by people on our team. Solar's electrical team is divided into 5 subsystems: power generation, power systems, the battery protection system, controls, and data acquisition. The power generation team worked tirelessly to make this car, well, solar powered. They designed and manufactured a 260-cell solar array that is used to capture the energy from the sun and provide up to 800 watts of power. Additionally, they created their own hardware and algorithms for the maximum power point tracking, or MPPT system, which maximizes this extracted energy. For this, the team has won research grants and has presented at a research poster session. Beyond this, they have worked on an IV curve tracer board to characterize the solar cell modules, an RTD board to monitor its temperature, and an irradiance sensor board to measure the brightness and intensity of the sun. The power systems team then worked on taking this solar energy and powering the rest of the vehicle. They designed, manufactured, and tested a 434-cell lithium-ion battery pack divided into 31 models of 14 cells, which in total can provide up to 130 volts. They designed the board that uses an isolated DC-DC converter to step down this voltage to power much of the electrical system. In addition to the lithium-ion pack, we are required to have a supplemental battery pack. For this, we use 10 1.2-volt nickel metal hydride batteries connected in series, which are used in startup to power the driver fans and radios, and also in case things go, unfortunately. The power systems team is also responsible for the wire harness. Prioritizing neatness and organization, they methodically designed and manufactured a wire harness, connecting all of the parts of the electrical system together. The battery protection system team's main responsibility was to then create a system to monitor the voltage, current, and temperature of the lithium-ion battery pack, a crucial task to ensure the safety of the driver. To accomplish this, the team designed, created, and tested their own software and hardware. On the software side, the team developed custom software running on a real-time operating system to continuously monitor the battery pack at 7 Hz. On the hardware side, the team created their own printed circuit boards to measure the 62 temperature sensors and 35 fast-acting voltage-sensing fuses attached to the batteries, a board to measure the current output of the battery pack using a shunt resistor, a board to control the fans in the battery pack, and a leaderboard to interact with all of these peripherals. One key focus of the team was in modularity, ensuring that this design can be used in future vehicles as well. The controls team then made sure that the car actually functions, well, like a car. One interesting aspect of the competition is the opportunity, as Rishi said, to compete in a cross-country race, in which solar cars will race on actual highways across the US. While we are not competing in this race this upcoming summer, we want to keep this a possibility in the future. This means that our car must be completely street legal, which the controls team ensured that we met. They developed their own software to run on a real-time operating system and hardware to control all of the driver's switches, pedals, headlights, brake lights, turn signal lights, hazard lights, and any other driver inputs. In addition to this, they interface with our over 95% efficient motor from Mitsubishi, which is designed specifically for solar car racing. They also implemented regenerative braking, allowing us to even save energy while braking. Last but certainly not least, the data acquisition team worked on developing programs to send real-time information about the car, information that will be used by the pit crew to monitor the status of the vehicle during the race. Using car from our custom telemetry board, which is populated with a GPS, inertial measurement unit, and a real-time clock, as well as data from the CAN communication line, they created methods for us to not only monitor the car, but to also assess its performance after the race. In addition to this, they created a dashboard and mobile acquisition team built on a Raspberry Pi, which will allow us to watch all the collected data in real time on any nearby device. This vehicle would not have been even a remote possibility if it were not for all the work that each and every one of our members put into this car, whether it be from the electrical, mechanical, or operation side of things. While I wish I could credit each person individually on stage because they all truly deserve it, I will have to settle for this. Thank you all for the work that you've done, and to the audience, thank you for supporting us. I think I can speak for everyone else who just spoke when I say we're all excited about what the future holds for this team. Thank you.
Thank you so much, y'all, for being here and for sharing this experience with us. The last thing that I would like to say, because they won't say it about themselves, is that these three people up here on this stage are some of the most amazing engineers that I've ever worked with, and this car would not be here or even close to what it is without them. So, one more, I promise only one more. Round of applause for Clark, Walter, and Hannah. And with that, I will pass it on over to Longhorn Racing's third team, the combustion team.
Our first competition was in 1981, and though it was only against a few other schools, the competition has grown since then and now includes over 800 schools worldwide and is one of the most world-renowned student engineering competitions. And though the competition has grown and changed in this time, our goal has not. Our goal has been and will always be to advance our members' engineering education. By giving people the opportunity to design, manufacture, and test their own components, they get the opportunity to learn much more about the degrees they're studying and also about how to make parts better, how to design better, and how to be a better engineer overall. So I'll talk briefly about the competition that we compete in. So although it's changed a lot, it's still relatively similar, and that is an engineering-focused competition, and it's not a driver's competition. We have 3 static presentations and then 4 dynamic events of competition. We have our cost presentation, our business presentation, and also our our design presentation, much like electric. And then we actually compete in the same 4 dynamic events. The only difference is the powertrain and some of the testing at the beginning of the rules. So we first compete in dynamics for acceleration, which is straight line performance. We then compete in a skid pad, which measures the lateral or sideways handling performance for our car. We'll then do an autocross run, which evaluates dynamics performance, and then endurance run, which, while still testing dynamics, makes sure our car can test up for a run that's a lot longer, see if it can take abuse. The way we manage our design cycle each year begins and ends with competition. So after the competition each year, our leadership for the next year will meet over the summer and discuss high-level goals. As they work together over the summer, they'll meet again in person in the fall to do recruitment. As we onboard people throughout the fall semester, we'll finish up a lot of our part design, and the end of the fall semester will feature a critical and a preliminary design review, not in that order. At those design reviews, we will invite alumni back, professors, and interested industry engineers, and they'll evaluate and critique our designs. There's typically a lot of critique there. And then at the end of that, we'll revise our designs to meet their critiques, and then begin manufacturing over winter break. If you're a Longhorn Racing parent and you didn't see your kid over winter break, thank them for their service. This is what made the car. After beginning manufacturing in winter, we'll typically finish in about mid-spring and begin initial testing then. Throughout the testing cycle before competition, we'll basically test as much as we can with our schedules and rebuild things and redesign them whenever they break. And they always do. That's valuable. Regardless, right after finals, we do a last bout of testing for our summer competition, which is in early June. And then the next year, the process repeats itself right over again. And I know I've just spent like a whole minute talking about how we got here, where we are right now, but now we're gonna step it back all the way to the beginning, after competition 2021. I'd like to introduce our Chief Engineer, Jonathan Parra, to talk about high-level design. Thank you.
Hey everyone, thank you Tyler. My name is Jonathan Parra. I'm the third year mechanical engineering student here at UT, and I'm the chief engineer for the combustion team. Starting our high-level design this year, we use a new mechatronics simulation software, AIMSIM, provided by Siemens, to create a virtual model of the 2021 car for testing in different dynamic events. Using this model, we tuned and tested it in different dynamic conditions, including an endurance/autocross track taken from the 2019 Michigan competition, a straight line acceleration run, and a skid pad or a figure eight. For each of these dynamic conditions, we defined success criteria that we could then use to train our model for finding new high-level parameters. For endurance, we chose farthest distance in a set amount of time. For acceleration, we chose fastest to 75 meters. And for skid pad or the figure eight, we chose maximum lateral acceleration. Taking these new high-level parameters, we then weighted them based on their relevance to the competition and created an optimized parameter set that our design engineers use to design, manufacture, and assemble the new 2022 car. Next up, to talk about the fundamental basis for our component level design, our dynamics lead Sam.
Hey everyone, my name is Sam Finley. I'm a third year mechanical engineering major. So similar to on the electric team, our dynamic system is composed of, or is responsible for the suspension, the wheel assemblies, and the overall handling characteristics of our car. So to provide some context for this year's design cycle, last year's car was finished pretty late and we had very little testing time before we had to leave for competition. So with that in mind, this year we set ourselves the primary goal of having the car done early enough that we could test it, fix anything that broke, and tune the car before leaving for competition. So we carried over some high-level suspension geometry parameters from last year's car. Is there any feedback? Okay. While adapting, so this year we carried over some of those high-level suspension design parameters while adapting our hard points to improve our steering feel, reduce the toe compliance of our wheel assemblies, and also accommodate our new shorter frame design for this year. So another design change we made this year is a switch from belt crank actuated to direct acting suspension. This is a simpler design that has fewer parts to manufacture and comes with the added benefit of removing one source of unwanted suspension compliance. Another development this year was some improvements to our finite element analysis strategy led by our wheels lead min over there. So we performed FEA on our control arms as well as doing full wheel assembly FEAs. These full wheel assembly FEAs as compared to exclusively part level FEAs is a more accurate simulation strategy that allowed us to save a lot of unsprung weight from our car. Another source of weight savings was our use of metal 3D printing, which was provided by one of our title partners, Cumberland Additive over there. So 3D printing allows us to design more complex geometries that are not manufacturable by conventional machining methods. And these more complex geometries can be lighter and stiffer than our counterparts from previous years. Another source of weight savings for this year's car was, or another new manufacturing method I'd say, is our use of carbon fiber tubes for our suspension linkages. This was done in collaboration with our brand new composites system composites team under the body system. And on that note, I'll hand it over to our body system lead, Tim, to talk about the next level of our design.
Howdy everyone, and thanks for the intro, Sam. I'm Tim Roy Chowdhury, fourth year chemical engineering student, and for this past year I've had the privilege of being the body system lead for the combustion team. Before I get into it, I'd just like to shout out each and every single member of body. Between all of us, we've pulled a bunch of endless nights up at Pickle and down here at the ETC garage, and thanks to y'all's dedicated effort, we've managed to put together a body system that I can say I'm proud of, and I hope that y'all can say the same as well. So just a massive round of applause for all of the body members. On top of that, I'd like to thank all of y'all supporters, parents, corporate partners for coming out. I know that it takes time out of all of y'all's schedule to come down and support us, but I'm sure for all of our students, just to see this many people vested in our success, it would mean a lot to them. So thank y'all for coming out as well. With all of that out of the way, let me take you through the design highlights for what Body did this year. Starting off, Liam Cosgrove, our aero lead, had the mammoth task of designing and simulating ground-up new aerodynamic package for the car, which is, by God, he did it. This is the first time we've done that in recent memory, and thanks to all the, I think, 500 plus CFD simulations he's done and all the testing plans we have put together, I'm sure that the car will do great at competition and the design event. His aero package includes a 2-element front wing, 3-element rear wing, and side pod, and all your associated bodywork like your nose cone and side panels. Next up is our frame lead, Isabella Garlow. She had the mammoth task of dealing with all the supply chain issues that came with trying to get the frame done on time, but she managed to pull it together as well. Highlights for our frame design this year, we've got a flat bottom so that if the aero team decides to implement an under tray next year, they've got the frame design ready for an implementation. They also cut out the rear box, a significant chunk of weight for the frame, and it also changes the dynamics of the vehicle a bit. And on top of that, we also added removable roll hoop supports to our frame. So that means whenever the engine team might need to take the engine out or do some maintenance for there over in the engine bay, we can just take the supports out of the way and make their lives like 100 times more easier. With that, I'd like to also talk about Ray and the composite subsystem this year, new under a body. They're a team dedicated to design and analysis of all the carbon fiber parts that go on the car. So Sam talked about it earlier. We've got carbon fiber push rods, carbon fiber tie rods, and all sorts of, obviously, new aero packages, all carbon fiber as well. And thanks to the efforts of them up at Pickle, and we put it together for this competition cycle. And last but not least, we got Rebecca, basically the one-man ergo team, or one-woman ergo team, pardon me. We put together a pretty good part optimized package this year for the ergonomic system. The topology optimization is massive in the pedal assembly, and thanks to our corporate partners Cumberland, we managed to print all the complex and organic shapes out of aluminum using their 3D printing technology. On top of that, working with the composite system, we managed to do some carbon fiber parts for the ergonomic system, namely the carbon fiber steering column, which is a significant weight decrease compared to the steel steering columns we'd run before, and a carbon fiber dash, mainly just because it looks cool and we like carbon fiber. And lastly, we've been integrating a lot of electronic stuff into the ergonomic system, namely a new in-dash display. Basically give the driver info they would need and when they want it and how they want it. And on top of that, paddle shifters so that the driver can just switch gears right on the steering wheel without having to take their hands off and possibly lose control. And finally, along with the paddle shifters, we integrated electronic throttle control so that we can have individual mappable throttle curves to driver preferences. And to speak about powertrain in general, now that we're talking about throttle, I'd like to introduce Blake, our powertrain lead.
Thank you. So, my name is Blake Titel. I've been on the team for the past 4 years and have been the powertrain lead for the past 3 years. So, the goal of the powertrain is to optimize the acceleration of the car out of and in between the corners of the FSA circuits that we race on. So, a good way of doing this is, in general, we break down all of our problems down to first principles. And a good example of this is our one-dimensional wave model. So the one-dimensional wave model we use is an engine model that we can use to correlate our inputs to our outputs. So in other words, we can correlate any changes we make to any part of the design of the powertrain and see what kind of performance gains we'll get out of it before actually implementing the design and manufacturing. And so with that said, once we have those kind of parameters from the model, we can create a 3D model, and then we can create a 3D model from that, and then perform flow simulations on that to further optimize the design. So both intake models that we designed were 3D printed by Cumberland Additive, and they were printed out of a nylon polymer. And this allowed for more complex geometries and more aerodynamic features inside the intake, which allowed us to improve pressure losses. So also printed by Cumberland was our fuel tank, which allowed us to reduce weight by about 70% compared to the conventional aluminum tank. So this was a big gain for us. Another new design feature is the dry sump oil system, which allows us to store the oil in an external reservoir instead of letting it pool in the bottom of the engine. And so this allows us to cut off the bottom of the engine essentially and lower the engine, which is the heaviest component in the car, by about 3 inches. And so if you can lower the heaviest component in the car by 3 inches, that does a lot for dynamic performance of the car. So our drivetrain features 3D printed aluminum differential mounts, also printed by Cumberland. And so the reason for doing this was that it allowed for a stiffer and lighter design, as well as reducing the manufacturing workload of our team so we can help improve the schedule and get the car done earlier. So in summary, in 2019, at the design event, powertrain didn't do so hot. We were, I think, bottom 20%. But the year after, we improved a lot, and this is last year, and we were in the top 20%. So this year, we go into competition hoping to be in the top 10%. So yeah, it should be a good year. Next up is Cyrus Electronics.
Thank you. My name is Cyrus Modby. I'm the current electronics lead here on Combustion. I am a senior studying computer science. So this year we had a big focus on telemetry for the car. We implemented a race capture system, which can take in CAN bus messages off of the engine computer, as well as our other custom boards, as well as various analog, digital, and dynamic vehicle parameters, and broadcast them live over cellular telemetry for analysis on the pit wall. We also run a Wi-Fi telemetry system, which allows us to view, manage, and configure our ECU on the fly while the car is still driving around. We also implemented a driver radio system this year, as well as an onboard GoPro for post-drive day video analysis. We've also worked on our wiring harness a lot this year. We have a very, very nice modular system, and we've also focused on knowledge transfer a lot this year. So we've had a big focus on documentation and also on visual wiring harnesses. So from the hardware side of things, I'd just like to shout out Francisco, the current hardware lead, and also my right-hand man for basically the past 2 years, as well as Kenneth Perry, who is the next hardware lead, and Logan Liberty, who definitely helped out a lot as well. So one of the first boards they worked on was the paddle shifters board, and that board basically actuated the paddle shifter solenoids in order to upshift or downshift the car, but it became a lot more than that. So it's connected to the engine computer and the other boards over CAN bus, and so it can detect money shift situations just to protect the engine. It also monitors bottle pressure, so we can send alerts to the driver or the pit wall if we reach kind of a critical level. Next thing he worked on was the BSPD, short for Brake System Plausibility Device. It's basically a regulatory device that checks that the throttle and brake aren't pressed too hard at the same time, and it'll take the car out of endurance as a safety measure if they are. So he also worked on a pre-BSPD, and that pre-BSPD will send a message to the engine computer before the BSPD trips, and it'll basically shut the throttle off so it doesn't take us out of endurance. Last thing he's working on is the driver's display board, which has different configurable modes. It ties into the engine computer and all the other telemetry, and so we can have something like a race mode, where it's basically only paddle shifters and warnings if they come up. and versus like an analysis mode while we're testing, where we can view many, many different parameters. So from the software side of things, I'd like to shout out Joey and Tejas, our current and new software lead. They have been working very hard on a live telemetry, on a telemetry server for post-drive day analysis. So we take the files from the race capture, we put them in the server, and basically we can kind of view and analyze with infinite possibilities. So we can have flexible axes, we can have that GoPro video kind of displayed side by side with the video going through. And it's also searchable by metadata parameters. So we can search for lap times that were only less than 1 minute and 15, just as an example. And they've done so much more than that. But with that, I would like to wrap up the System Lead's presentation, and I'll hand it over to Ty for a couple final words.
Hi. All right. The more observant amongst you might have noticed that there's no car here. I promise. We finished one. The even more observant might have noticed the thing coming in the back. The EER had a very specific rule. If we brought the car in, it couldn't have fluids in it. But if there's one thing the combustion team is good at, it's making a lot of annoying noise. And that requires fluid. So, without any further ado, I'd like to officially unveil our 2022 car, codenamed Friendly Goose. With that, thank you all for coming out today. We really appreciate it. Show us appreciation for all the hard work we've done here. We'll be here for another hour. Please go around, talk to us at the cars, grab some food. And thank you. You have a great day.